My name is Jennifer Van Saters. I'm a graduate student at The Ohio State University. I'm here to talk to you today about a paper that I've been working on with Mark Pinsonneault, in which we investigate the ways in which stellar rotation can be used as a diagnostic of underlying stellar populations. The stellar rotation is a very strong function of mass, age, and evolutionary state. And in the era of satellites such as Kepler and Corot, we'll have measurements of rotation periods for tens of thousands of stars. And we can start to think of rotation measurements as more of a standard observable than we ever have in the past. And because rotation is sensitive to parameters such as mass and age that are otherwise difficult to measure, it becomes a very interesting observable to focus on. So in order to understand how we expect rotation to behave across the HR diagram, we've constructed a set of theoretical models. And these models have initial conditions that are motivated by the observed periods in open clusters as a function of mass, and that are evolved forward under simple assumptions about angular momentum evolution. In this figure, I show the behavior of our models at two representative masses to highlight the differences between hot and cool stars where rotation is concerned. Cool dwarfs, below 6200 Kelvin, have deep convective envelopes and lose angular momentum on the main sequence and subgiant branch, and as a result they are slowly rotating for the majority of their lives. Hot stars, on the other hand, have very thin convective envelopes and weak magnetic braking and angular momentum loss. They're therefore born rapidly rotating and remain rapidly rotating on the main sequence. Both sets of models spin down substantially on the subgiant branch. Here, both mass regimes host deep convective envelopes and undergo magnetic braking, and the moment of inertia increases due to envelope expansion. Both of these effects result in an increase in the periods. When we combine many masses together and place them on a modified HR diagram, we see the following picture. Here, color encodes the rotation period, with red representing rapid rotation and blue slow rotation. The break between hot and cool stars on the main sequence persists onto the subgiant branch. The rotation periods, even on the subgiant branch, are strongly mass dependent. We can therefore use rotation as a means to constrain the stellar mass. We have identified three distinct period regimes, each of which are populated by different sets of stars. Objects with periods of 10 days or less are either young, low-mass stars, or high-mass stars that are rapidly rotating both on the main sequence and beginning of the subgiant branch. Objects with periods between 10 and 40 days are either cool dwarfs or crossing subgiants. The dwarfs in this regime have a tight relationship between period and age and are suitable for gyrochronology. However, in magnitude-limited surveys, the fraction of subgiants in this period range can be around 30% for a magnitude limit of G of 14 around solar effective temperatures. This implies that one must have information about the evolutionary state of stars before gyrochronology can be used to determine ages. Although the main sequence and subgiant branch both have period-age relationships, they are not the same, and there is substantial subgiant contamination. Finally, objects with periods of greater than 40 days are subgiants, typically of low mass. In addition, we've identified a period-radius relationship on the subgiant branch, and this is because both period and radius respond to the expansion of the stellar envelope. This is particularly interesting in the case of exoplanet host stars, especially those that host transiting exoplanets, because there a precise determination of the stellar radius is very important for understanding the planetary parameters. And here we can use period as a constraint on the stellar radius. Now that we also have this set of predictions that tells us how we expect things to be rotating as a function of their location on the HR diagram, we can look for objects that deviate from these trends. Slowly rotating A stars, synchronized binaries, or blue stragglers could all be objects that you could pick out as unusual based on their rotation periods. And finally, now that we have these set of theoretical predictions and large data sets that are becoming available, we have the opportunity to compare the models and the data and to improve our angular momentum evolution models. So if you'd like to hear more detail about the things that I've discussed today, we encourage you to take a look at our paper, which is posted on the archive.